Hey guys, Mr. Mar with the second video over improper integrals. So in this video, we're going to cover when we have a discontinuity as one of the limits or our interval takes us through a point of discontinuity. So for the first example, we have this integral of 1 over x to the 1/3 from 0 to 1. So obviously, if we substitute in 0 for x, we get 1 over 0, which is undefined. So our limit produces a discontinuity. So the way we handle this is we're going to have the limit as a approaches 0. And if it's the lower limit, we have to approach the lower limit from the right. So the limit as a approaches 0 from the right of the integral from a to 1, we're going to make this x to the negative 1/3 dx. And when we integrate this, we're going to get the limit as a approaches 0 from the right of, so we're going to have x to the 2/3, and then we're going to divide by 2/3, which means we end up multiplying by 3/2. We evaluate that from a to 1. So if we substitute in 1, we're going to get, so we'll keep our limit in for a moment, the limit as a approaches 0 from the right. If we substitute in 1, we're going to have 1 to the 2/3, which is 1 times 3/2. So we're just going to get 3/2. And then minus, so if you approach 0 from the right, you're going to get an increasingly small value. You're going to take the cube root of that and square it. So eventually it's 0. So if we get really close to 0 but not actually get to 0, we're going to get 0. Now remember, the easiest way to take a limit is substitute in that value. So if we could just substitute in 0, we get our limit. And in this case, we can do that. If you substitute in 0 for x, you're going to get 0 to the 2/3, which is 0, times 3/2, which is 0, so minus 0. So our limit is 3/2. So even conceptually, if we could not substitute in 0, we could, one of the things that we could do is look at this graph or look at the table, which is even more helpful. We'll have 1.5 x to the 2/3. And we'll look at a table instead. So we're going to increment by 0.01. So when we get really close to 0, our values approach 0. And if I did this as like 0.00, I need to do plus 0.00001. And so we can really see what happens is when x approaches 0 from the right, we get these incredibly small values that approach 0. So like this is 0.000007. And so again, when we approach 0 from the right, this converges to 0. Now again, we can just substitute in 0, but in some of these it's going to be impossible to substitute in the limit. So I want us to understand how we arrive at our conclusions if we can't substitute in the value. So for example 6, we still have a 1 over x cubed, and in this case we have a 0 in the denominator, which is our point of discontinuity. All right, that's better in focus. All right, so the first thing is we're going to make this the limit as a approaches 0 from the right of the integral from a to 1 of x to the negative 3 dx. And when we integrate x to the negative 3, we're going to have the limit as a approaches 0 from the right of x to the negative 2 power divided by negative 2. So we're going to put a negative, we're going to divide, we have a and we have 1. And so again, improper notation coming up right now. So bad notation is us having just negative 1 over 2x squared evaluated from we'll put 0 to the right and 1. Now, we can still make sense of this, though. This equals, so when we substitute in 1, we're going to have -1 divided by 2. So that's just going to be -1/2 minus, so if you take a number really close to 0 and square it, you're going to get an even smaller number. And that smaller number divided into -1 is going to blow up to infinity. And we'll see that again if we look at a table. So we're going to say -1 divided by 2x squared. And we're going to look at our table. And so again, when we look at this, we see these values that are blowing up to infinity. This is like -5 with 9 zeros behind it. So it's like -500 million, 5 billion maybe. But either way, so these numbers go out to infinity when x approaches 0. So this is going to be -1/2 minus infinity. So that's just going to equal does not exist because the limit doesn't converge. The curve doesn't converge. So in this case, we ended up with an infinite limit because a very tiny number divided into -1 is going to be infinity. So -1/2 minus infinity is a limit that doesn't exist. For example 7, we're going to have a case where we have to do u substitution and possibly rewrite our integral. So when we substitute in 0, that's not a problem. When we substitute in 27, also not a problem. We actually divide by 0, which we can't do. So the first thing that we need to do is to integrate this. We're going to do a simple u substitution of 27 minus x. And so our du is going to equal negative dx, so that negative du equals positive dx. The next thing is our x limits are from 0 to 27. Our u limits are going to be, if you substitute in 0, we're going to get 27. And if we substitute in 27, we're going to get 27 minus 27, which is 0. So the rewrite on this is going to be the integral from 27 to 0 of negative, we're going to say, all right, so this is to the 1/3 power on the bottom. We're going to move it up and say u to the negative 1/3 du. So when the lower limit is the larger, we can flip the integral over and make it positive. So what we're going to do is get the integral from 0 to 27 of u to the negative 1/3 du. And again, all we did was switch the limits and then multiply by -1 to get rid of that. So I think we did this one in the first example. We're going to get 3/2 u to the 2/3, and we're going to approach 0 from the right, and we're going to go out to 27. So when you substitute in 27, you're going to get the cube root of 27, which is 3, squared, which is 9, times 3/2, which is going to be 27 halves. Let me do that math again. Cube root of 27 is 3, squared is 9, times, it's 27 halves. And so then when we substitute in 0 from the right, I mean, again, we can just substitute in 0 because we're not, it won't be undefined anymore. So 0 to the 2/3 is 0 times 3/2 is still 0. So this limit is 27 halves. So while it is improper notation to write our integrals like this, in my opinion, the notation is a little hacky and it makes the problem long. So I am totally fine with you doing this instead of doing this, as long as you get the correct answer. So in this case, the limit converges and we get 27 halves. Example 8 is, what do we do when we have a point of discontinuity inside the interval? So we're going from 0 to 3, and if we look at the denominator, we see that x equals 1 is a point of discontinuity. So what happens is we split our integral into two separate ones. We get an integral from 0 to 1 And that's going to be x minus 1 to the negative 2/3 plus another integral from 1 to 3 of x minus 1 to the negative 2/3. I forgot my dx in both of them. So if we did a u substitution, look, we get u equals x minus 1, so du equals dx. And so this is just going to be u to the negative 2/3 instead. We don't actually need to replace this because it's a trivial substitution. So when we integrate, we're going to get, let's see, x minus 1. So if we add 1, we're going to get to the positive 1/3. So that's going to be to the 1/3 power divided by 1/3, which is going to be a 3. And we're going from 0 to 1 from the left. Because if we approach the upper limit, it has to be from the left. And then we're going to have plus the exact same exact same result, but it's from 1 to the right and to 3. So for this first thing, we can, as long as we can substitute in 1, it's fine. And again, we can because we don't have a point of discontinuity at 1 anymore. So when we substitute in 1, we're going to get 1 minus 1, which is 0, to the 1/3 is 0, times 3 is 0. So we get 0 minus, if you substitute in 0, you're going to get the cube root of negative 1, which is negative 1, times 3 is a negative 3. So we get 0 minus negative 3, which is positive 3. Then plus the result from this other integral. And when we substitute in 3, we're going to get 3 minus 1, which is 2. And so we're going to have 2, the cube root of 2 times 3. So this is going to be plus 3 times the cube root of 2. And then when we substitute in 1, we're going to get minus 0 again. So this evaluates to just be 3 plus 3 cube root of 2. Now again, because we can just substitute in 1 in both of these because it's not a point of discontinuity for this integral. And so then for the last example, we have f of x equals 2 ln x. And we have R's is unbounded region in the fourth quadrant of f, but between f and the x-axis, and we want to find the area. And secondarily said, like, find the volume if the region is rotated around the x-axis. So the graph of y equals 2 ln x is, let me clear this out, 2 ln x. Let's see, we graph this. So we want, let's zoom out. And so I want you to see, we want to zoom in here. So when this curve gets really close to the x-axis, y-axis, but it never touches it. So when it says unbounded, it means this region that continues downward. If you remember in functions analytic geo, the ln you can't have 0 as an input for the natural logarithm. You can get really close to it, but you can't actually have 0. So what we're looking at is a curve that goes through 1, but it gets very, very close to the y-axis without ever touching it. So this is the unbounded region. So when we're trying to find the area, we're looking at the area that's bounded between the x-axis and this. So we're going to have the integral from 0 to 1 of 2 ln x dx. So now obviously we never actually get to 0 because x can't be 0. So what we need to see is what happens when x approaches 0. And that's going to require us to look at a calculator and look at a table and see what happens. So the ln x part, this is one of these things that we had to do integration by parts with, if you remember. So we're going to let our u equal the ln x, because u is always the ln x because of this rule, Lipit. So u equals ln x, dv is going to be dx, v is going to be x, and du is going to be 1 over x dx. So when we integrate this, right now we're just going to say we get, the 2 is going to hop out to the front. So we're going to have 2 times, so we're going to have x ln x. So x ln x minus, we'll put this in parentheses, minus the integral of v du. So that's just going to be x times dx over x is just going to be minus dx. And so we're going to have 2x ln x minus 2 times the integral of dx. And when we integrate that, we're going to have 2x ln x minus 2x evaluated from 0 to the right and 1. So if we look at this curve, we're going to just put this in. We're going to have 2x ln x minus 2x. We're going to go to the table. And so when we are approaching, so we'll do plus 0.001 instead. So when we approach 0 from the right, these values, if we're coming downwards, these values get smaller and smaller and they approach 0. So we'll add one other 0 so you can see this. So as we approach 0, these values get smaller and smaller. And if we did one more plus, so 1, 2, 3, 4, 5, we'll do this. These values get incredibly close to 0. So this converges to 0, and this is also going to converge to 0. So for the upper limit, if we substitute in 1, you're going to have 2 times the ln of 1, which is 0, minus 2. So that's just going to be negative 2. And when we approach 0 from the right, you can substitute in 0 right here, and you get 0. And here, this is going to converge to 0. So we're going to have minus 0. So this area is negative 2. Now, again, the negative 2 makes sense because the area is below the x-axis. So this converges to negative 2 in terms of area. So that concludes this video on improper integrals when our integral produces a point of discontinuity at one of the limits or as we go through the integral. We'll talk about recs in class.